Welcome to another episode of Quintus Technologies Tech Talks. I'm Chad Beamer, and today I'll be interviewing a research assistant representing one of Germany's largest universities. Without further ado, could you introduce yourself, discuss the university and facilities, as well as highlight your area of focus?
Thank you, Chad. Thank you very much for having us and inviting us to the Quintus Tech Talk series. It's been a pleasure. My name is Benjamin Ruttert, and I'm working since 6 years as a research associate here at the Ruhr University in Bochum, one of the 10 largest universities in Germany. Since 2014, I'm in charge of the Quintus QIH9 R&D lab unit that was installed here in Bochum, and I'm related to all the HIP activities that are done here in Bochum. A good thing working here at the Institute for Materials at the Ruhr University is a quite solid infrastructure we have here for R&D. We have all access to all the state-of-the-art characterization methods because as a material scientist you are always interested in the innovative processing routes, the evolving microstructures, and of course the properties that are a result from these processing routes. My main research area is about high-temperature materials for mission-critical applications, such as turbine blades or turbine blade materials for aero engines or power generation.
Benjamin, both long-term projects and extremely comprehensive. Can you speak in a little bit more detail on the scope of the nickel-based superalloy work that you had mentioned?
Of course. So our main goal is to improve the thermal efficiency of gas turbines and make them more efficient and reliable. And in order to achieve this, we have to look onto the most severe areas of gas turbines. And this is behind the combustion chambers where the single crystal nickel-based turbine blades operate. And then in order to improve the properties of these materials, or this class of materials, we can look onto the processing routes. And in a large industrial scale, they are cast as single crystals by using the Bridgman technique. And during casting, porosity forms, we have a chemical inhomogeneity, and afterwards the material has to be heat treated in order to homogenize the materials. The heat treatment is done in a conventional vacuum furnace. And the problem here is that we still have the porosity maintaining. And during homogenization, also porosity can form, a new class of pores can form, the so-called homogenization pores. So we have a lot of porosity introduced, and this means hot isostatic pressing has to be placed somewhere behind or before the heat treatment. And this is an additional processing step. This costs, of course, a lot of time and money. And also a very negative aspect of the older HIP units that have been used by the industry in the past are very slow cooling rates. And slow cooling rates are associated with microstructural coarsening. And of course, the machine is unproductive when you cool down very slow. And here we saw a lot of problems in the past and looked for a solution. And then we did a little research here and found that Quintus has a new technology provided with this fast cool capability. So there we decided to buy a small lab scale HIP unit, this QIH9 model with ultra rapid cooling capability. And this brought up many new possibilities for us. And there we found a lot of research that has been never done in the past, and then we started to look onto the influence of all the parameters that we have here during the HIP heat treatment.
Benjamin, you've mentioned some of the key challenges associated with the conventional route, and let's call it the opportunity that an integrated HIP and heat treatment cycle may offer. Can you go into more details on those benefits? Both from a processing route and material and performance route?
Yeah, sure. So the integrated HIP heat treatment or the high pressure heat treatment, of course, it is very beneficial when it comes to the processing itself. So we can perform the heat treatment and the hot isostatic pressing in one single step. When it comes to nickel-based single crystal superalloys, this means that we can perform the solution annealing, which is very extensive and very careful to do heat treatment, and apply simultaneously a pressure into this process. And then we can homogenize all these chemical inhomogeneities, but also shrink the porosity in one single processing step. And this, of course, saves a lot of time and money and we have a beneficial effect on the mechanical properties, because in the end, after the solution annealing or the holding step, we can quench down very rapidly. And this is a very positive influence on the microstructure that evolves during this cooling from the high temperature HIP regime, because we establish a very fine and uniform gamma-gamma prime microstructure after quenching. And this has a very positive effect because we precipitate very fine gamma prime cubes, and when we age them, they grow to a final size of, I don't know, 350 nanometers we found out. And this is a bit smaller than after conventional heat treating, because then you obtain a microstructure having a gamma prime edge length of about 500 nanometer. And this has a positive effect on the creep life of the material, because a very fine and uniform gamma prime microstructure after heat quenching has a beneficial effect on the creep life, because the material deforms a little bit slower and then creep life is improved. In addition, we have no porosity in the material, and this makes correct initiation and propagation very difficult, and therefore also the materials or the components' lifetime can be improved. So there are two very beneficial effects of an integrated HIP heat treatment. You save time and costs, but also you get improved microstructures, no porosity, and a uniform and fine gamma-gamma prime microstructure.
So this integrated HIP and heat treatment route gives one the opportunity to cut lead time, potentially cut cost, and also end up with a more ideal microstructure that lends itself to improved mechanical properties. So very impressive. Do other manufacturing techniques such as equiax and directionally solidified castings, as well as additive manufacturing microstructures, have the opportunity to also benefit from this route?
Yeah, definitely. So the good thing is we are looking or focusing on single crystalline microstructures or single grain microstructures. So they're very sensitive when it comes to heat treatment. You have to be very careful, select the temperature tolerance quite tight and all this stuff. And as soon as everything works out in the single crystalline universe, let's say it like this, you can also break it down to, let's say, more simple microstructures like directional solidified or columnar grains, but also polycrystalline microstructures. Of course, there are other aspects we have to keep in mind. It's not that simple, but as soon as something works out for the single crystals, we can also use this knowledge easily for the other systems. And even additive manufacturing is a really good point, Chad. So additive manufacturing is a growing industry, and it's very interesting to see how it evolves. And we are definitely aware of that. And in our collaborative research center, our colleagues from Erlangen are working on that topic too. And they are able to build single crystalline microstructures out of the powder bed. So you have a single crystal in the core and a polycrystalline shell. This is the nature from the process itself, but at least we have a single crystal in the core. This is really impressive. And the very interesting fact is here that everything is on a much smaller scale, because the solidification rates are much higher as in conventional castings. This leads to a very fine and uniform microstructure. However, it still obtains all the microstructural defects we also find in conventional cast microstructures. We have porosity, we have also gas inclusions, we have small-scale chemical inhomogeneities, and this means we still have to post-process the materials, and we can also obtain cracks during processing. It's for sure. And the very interesting part is here that we also developed a very short heat treatment in the HIP for this class of materials, because everything is much finer. You can also shorten the heat treatment time. And here we have developed a very efficient heat treatment in the HIP integrated, which takes about 45 minutes of holding time in comparison to 8 hours for a casting material, which is impressive.
So Benjamin, it sounds like you tackled the more challenging structure first, and then using those learnings to leverage it towards other material systems. And the AM single crystal work sounds fascinating. I can't wait to see the outcome of that work, the literature publications that are going to be produced. Beyond that, can you provide some additional teasers, specifically around the work that's been performed on rejuvenation of turbine blade alloys.
Chad, this is a good point. Rejuvenation is really important now in our times here. We have the very expensive single crystalline materials. A lot of expensive raw materials such as rhenium or tungsten are alloyed, and also the blade itself costs a lot of money. And when we look onto a turbine blade after service, it can show an internal and an external degradation. And the rejuvenation focuses on the internal degradation, because after a certain time in service we have a microstructural coarsening. The gamma prime cubes evolve towards a directionally coarsened microstructure, the so-called effect rafting. And we can also see micropores evolving, the so-called creep porosity or micro cracks that can form after creep or fatigue damage. And the rejuvenation has a goal to re-establish the microstructure that has been before service. And here we have done a lot of work also in the past. Of course, rejuvenation is nothing new, so in the past there was a lot of work and efforts been done to do it in a conventional HIP unit, or to do it in a vacuum furnace, or even combine it a little bit in the furnace and the HIP. But we made the approach to do everything in the new type of hot isostatic press with a fast cool capability, and there is a lot of interesting results and outcome from that. So we are able to re-establish the gamma prime microstructure. We can close all the pores that have formed after service. But the most important thing is that we maintain a single crystal after the HIP rejuvenation cycle. It's always a big problem when you introduce deformation into the material after service, after creep, degradation or fatigue. So we have designed a tailored rejuvenation HIP treatment that is able to maintain the single crystal microstructure too. And very interesting also is that we can restore the creep life of the material. For instance, when we do a creep test, interrupt it, look into the microstructure, characterize everything, rejuvenate it in our HIP, and then we do another creep test. So the creep properties have been reproduced, even though the material was elongated about 2%, for instance. And it's very promising, and now it is up to us to bring this or push it more into application, of course.
That's very impressive, Benjamin, and it highlights, again, an opportunity to use modern HIP equipment with high pressure heat treatment capability to reduce processing time, to optimize the microstructure, and eliminate porosity while maintaining a single crystal structure. And I'm assuming, again, this work, the result of this work, could be leveraged for other material systems, including AM.
Yeah, sure. As soon as you find out that it works on the castings and you are able to close the defects and re-establish microstructures pre and post service, you can of course transfer it into to the AM. But anyways, you have to keep in mind or be aware of that AM is another processing route or itself, so it can introduce high level of dislocation structures, for instance, and then you have to be more aware of recrystallization, for instance, because the solidification conditions during AM are quite different than in conventional castings. But we are on a good way to tailor this rejuvenation treatment for AM microstructures as well. Because the good thing about using this HIP hardware and the HIP equipment is that you can provide or you can program very careful selected heating rates, very accurate temperature holding steps with tight tolerances of ±2 degrees C, and this allows us also to rejuvenate AM microstructures that are very sensitive, for instance, for recrystallization. It is also worth mentioning that we are also can perform rejuvenation treatments for titanium aluminides, for instance.
Very exciting. The flexibility that a modern HIP vessel offers is going to result in some outstanding work that's going to be produced by you and the university. Benjamin, it's been a pleasure chatting with you today. The quality of the work being produced by you and Ruhr University of Bochum is second to none. I would like to thank you for your strong collaborations over the years, and we, Quintus Technologies, very much look forward to seeing some of the new work you're going to be producing in the near future. Thanks once again.
Chad, thanks for having us. It was a pleasure having this interview, but also working together with Quintus over the past couple of 6 years or so. It's been a pleasure. So always great support from you and your colleagues. The field service engineers always helped us in the beginning when we installed the unit, and we are now able to produce this high quality results. So thank you very much for that. And of course, we are always happy to collaborate with some other research institutes or end users to share our knowledge and to expand all the knowledge in the future. Thank you very much.
You're welcome, Benjamin. Thank you.